Good morning. Let's see how many colleges have joined us. I'm sorry for the slight delay, probably about 4 or 5 minutes. So we already have 20 colleges with us. Uh, I hope more will join. Now, I'll start. This was, as you people all know, we have a series of 15 lectures. And this was a part in this QEEE experiment, or we tried to have these classes. Now, today is my 14th class. So the last class for this course, the farewell class you can call it, this will be on Tuesday, which is I think 25th or 24th of March. 25th I think. So that will be our the last class. Today I will wind up. Let me just give you a scheme what we are going to do. Today I will wind up on shear force diagram and bending moment diagram. I had taken up an example and I am very pleased that at least 2 students responded. They sent their figures to me, which I will discuss today. I'll finish up this in about, let's say, 10 to 15 minutes. And then I had an option of taking one of the 2 topics. Either I could have taken up friction or a topic on distributed forces, that is center of gravity. And I have decided that in the remaining 1.5 hours or 2 hours, I will talk about friction. And there's a particular reason why I want to do that. Because what I find is when we teach friction and when students solve problems, there are a lot of common mistakes which people make, even in the students who come here after clearing JEE. At IIT, I find that there is a lot of misconception. So we have to make you unlearn what you have learnt about friction. But that's later. Let's first straight away come to the topic of the shear force and the problem which I had posed to you, and I'll give you the solution. Now there were 2 students, Tanvi and I think Mrinal. These 2 people, they sent to me they sent the solutions to me. Tanvi's solution was almost perfect, but there was a small calculation error, because of which there was an error. But what I would like to point out is that if you understand the concepts, then even if you make a calculation error, that calculation error can show up and you will be able to realize by drawing the shear force and bending moment diagram that you have made the error. So let's, without any ado, let's have a look at what our problem was, and I'll just draw the final free body diagram. On the beam which we had, there was a support force of 14.56 kilonewtons, and then at a distance of 8 meters, there was a point force of 10 kilonewtons, and also for the next 8 meters of the beam, we had a distributed force, a uniform distributed force of 2 kilonewtons per meter. And at this point, so this was point A, point B, point C, point D. At point C, there was also in the effective loading a force of 2.5 kilonewtons meter, a moment, sorry, not force, a concentrated moment. And then we had the final reaction at the other end, which was 11.44 kilonewtons. And I asked you to plot the shear force diagram and bending moment diagram for this. We had started the solution also earlier, and now let's see how this works. So we'll start with this solution. I'll just keep this loading diagram here and let's draw the shear force diagram. So we'll talk of, on this axis we'll plot shear force, let this be the 0 point, and we'll plot bending moment. My figures may not be up to scale, but we'll just do these, and then the explanations I'll write on the right hand side. So, and now because we have done this topic, I think we can just start this. So now let's see. So now the first section we cut from 0 to 8. What can we say about the shear force? Shear force, there's a force of 14.56, so that means V will be equal to 14.56. So when I go from 0 to 8, so this is each of these two units here is 8, so this is 8, 16, 24. So from 0 to 2, this shear force is 14.56. The bending moment M, this will be 14.56x. So we start, it's a straight line, it starts from 0 because there's a point support, there is no moment, and the moment comes out to be 14.56x. And the way to see it is, we have started in the loading so far, we have V here, we have M here, and then if I use my rules which I had discussed, so if there is a force of 14.56, a positive force, it causes on all elements to its right a shear force of plus 14.56. I get that. If there is a bending moment, the bending moment is a force P causes a bending moment of P zeta. So now the zeta here is nothing but x. So this is what I get at from 0 to 8. Is that clear? So this part was the easiest part. Now let us go from 8 to 16. Now from 8 to 16, if I draw the free body diagram, what I have is 14.56 at a distance of 8. First I have a 10 kilonewton force. Now my x is a section somewhere here. For the second part, x is lying between 8 and 16. So the x is somewhere here. Now what I have is, I have a distributed load which is acting not along the full length, only along this length. What is this length? This length is, the total distance is x, this distance is 8, so this length is x minus 8. I hope that is very clear to all of you. And this force was 2 kilonewtons per meter. So now, having drawn this free body diagram, that means in this free body diagram, the shear force and bending moment will look like this. There is a V and there is an M. Now let me start writing the expression for shear force. So first I have this 14.56. So I will have, this is positive, so 14.56. Now in this section I see a 10 kilonewton force which is downwards. So I get a contribution of minus 10. So this minus 10 is going to come just after point B. That means what is going to happen in the shear force diagram? The shear force diagram will undergo a jump of 10 kilonewtons in the negative direction. So that means here it will undergo, because of this point force, it will go down by 10 kilonewtons. That means this value will be, here this value is going to be 14.56 minus 10. So it will be plus 4.56. And then if I add up now, what is the contribution of this distributed force? First of all, we realize it is downwards. That means the sign will be minus. And how much is the force? This is 2 kilonewtons per meter. So minus 2, and we have to multiply it by the length for which it is acting, which is x minus 8. So this is what I will get in my shear force diagram. So the value of shear force will become 14.456 minus 10, which is 4.56 minus 2x plus 16. So this is the total value which I am going to get. And when I put x is equal to 8, or sorry, when I put x is equal to 16, what will happen? Because now, see, this distribution is going to continue up till x is equal to 16. So what I realize is, in the shear force diagram, I will get a straight line which will go down, and the end value will be the value which I get in this equation if I put x is equal to 16. So when I put x is equal to 16, I don't know if I have worked out this number or not. you put in this value. When you put x is equal to 16, this number will come out to be 11.44, which was the final number. So that means we have to go down till minus 11.44. So from here we draw a straight line and this number will turn out to be minus 11.44. Now I have not done any calculation. How do I know this number is minus 11.44? Because if I look at the remaining part of the beam, there is only a single force 11.44 and nothing else in the shear force diagram. So therefore, in fact, from here I can also conclude that the shear force diagram from 16 to 24 will be just at the same value 11.44, and this you can also say I could have gotten in by cutting a section between 16 and 24 and looking at it from the right. So you need not follow only one method. You can use composite methods, and this is how your shear force diagram will get completed. So that means the shear force when 16 is less than x is less than 24, shear force will be simply 11.44. Or the other way of getting it will be, we put it as 14.56 minus 10 minus 2 times. Now in this section we would have crossed this whole distributed force, so we just subtract the total value of this, which is 16 newtons, and that is how we will get the shear force. Okay. Now the more complex part is the bending moment diagram, and you also realize this minus 2 times x minus 8 is nothing but the integral of the loading. The loading was 2 uniform. When I integrate that, I will get 2x, and when I put in the limits it starts from 8, so I will get, there's a minus sign, 2 times x minus 8. So in the last class I had also done the function that if you take the area under the loading, that gives you the shear force. Area under the shear force gives you the bending moment, unless of course if there are some jumps. So now let's look at the bending moment here. For the bending moment I go back to this diagram and I use my rules. Let's work out. 14.56 will cause 14.56x. Then we have 10, it is minus, so minus 10. Now what is the distance between the cut section and this? So this total distance is x, this is 8, so minus 10 times x minus 8 is what I will get in the bending moment here. Now I also have to include this section. In this section the force is, this is a negative this thing, so therefore the force is minus 2 times x minus 8. This is P. Now what is the effective distance at which this force is acting? 2 times x minus 8 from the cut section, and we realize it is acting at a distance of x minus 8 divided for the total expression for bending moment, that m is equal to 14.56 x minus 10 times minus 8 minus 2 times x minus 8 multiplied by x minus 8 divided by 2, and you simplify this expression. So what it tells you is that the bending moment will be a quadratic curve. Now when we draw the diagram for the bending moment, then we realize it is going to be a quadratic curve. So now what is happening to the bending moment? Let's have a look at this. So we have it as minus 2 times x minus 8. What happens to the bending moment is, at this instant we have minus 10 times x minus 10 times 8. So now the bending moment will start to rise and then it starts to fall. So this is how the bending moment diagram, it takes a quadratic shape. See, what you realize is when you simplify this expression, this takes a form of y is equal to minus x square. The quadratic term is minus x square, then I think it is minus 20x or minus something x, and then plus some. something. There will be no jump in the value of bending moment. In Tanvi's solution, what she had done was, the mistake which was made was that in calculation of this bending moment equation, a slight error was there. And that is why when the moment value was calculated, just before it and just after it, there was a small jump. Now, qualitatively you should know that unless there is a point moment, there will be no jump in the value of the bending moment. That means if you are getting a jump in the value of bending moment at x just before 16 and just after 16, you have made a mistake. You please recheck your calculations. Also, you realize I have shown this curve like this. How do I know, or where does this maximum point come? And for this, we look at the expression d by dx is equal, dm by dx is equal to v. So that means the point where v is 0 gives us the maximum point. So this maximum is going to correspond to the point where the shear force becomes 0, and after which the bending moment then starts to fall. And this quadratic curve, you work out the values at x is equal to 8 from this expression and x is equal to 16. You get this. Now, from 16 to 24, what happens? What we see in the loading is that there is a clockwise moment of 2.5 kilonewton meters. So what will that do to the shear, to the bending moment diagram? This moment will do nothing to the shear force diagram, but it will cause a jump in the bending. This is a clockwise moment. So here there will be a jump by the value of m1, which is equal to 2.5. So therefore, at this point there will be a jump, and after this, what we realize is on the right side we see there is only a single force, nothing else. That means it has to be a straight line. So this will here, from here, go to 0. So this is how the bending moment diagram will look. And if you want to actually work out the expression for bending moment, then we can work it out. Either we can take it from the right side. So therefore this will just become equal to 11.44, and it is times, this is total, this distance is what we are calling x, the total distance is 24, so this times 24 minus x. So this is how the bending moment will finally appear, and you will get the same expression if you start from the left. So therefore we use multiple of techniques to get to the shear force and bending moment. Okay, I'll now like to just interact with some people before I go to the new topic. I've just put up this solution, and maybe I will also put this up in detail on my QEEE web page. But before that, let's try to see if I can. Let's first start with CE Pune, because that is where the student was from. Is it there? Is Tanvi there? The student who sent me the solution. There was a student who had sent the solution. Tanvi, could you please come? Okay, that's it. Hello? Yeah, yeah. The picture is not very clear. Are you Tanvi? No. Okay. Who is the person who had sent the solution to me? You did? Was it you? Were you the person who sent the solution? Did you send the solution? Well, you did a nearly perfect solution. Let us all have a round of applause for Tanvi. Because, but now do you realize that small mistake which you had made and which could have been caught because of the fact that you would have realized that there should be no jump?
Yes, I got it.
Do you understand? Okay, good. So I'm sure now you'll not make any mistake if you get a similar problem in your exam or you have to use it later in your life. Can I be sure of that?
Yes, sir.
Okay, great. Thanks. Now, has everyone understood the solution? Okay, have you people understood this solution which I have sent or which I did in the class? Okay, any other place maybe let's try to. If there is. नहीं है चलो okay that's fine. LNMIT नहीं है okay. Yeah, can I interact with someone at LNMIT? Is this LNMIT Jaipur? Hello? Let's see, I think they're trying to come. Did they have the mic? Do they have the mic or no? Hello, yeah, LNMIT Jaipur. You seem to have a very big auditorium and very few students. Hello? Yeah, are there any doubts? Are there any questions?
Hello.
Yeah, hello. Yeah, okay, I can hear you now. Are there any doubts or questions on this?
No, sir, no, sir. It's very clear, and all the students get clear understanding of the solution and process. So there is no
Okay.
issues.
Okay,
Thank you,
thank
sir.
you. Thank you very much. It's good to hear this. Okay.
Thank you, sir.
Okay. Okay. Now, okay, I think I'll just get back to the class. There's one more thing I'd like to discuss, just a small thing. Suppose okay. You may come across, most of them are like that. You may come across a loading which is linear. Linear, which means not flat. So that means W of x is of the form a times x minus x0, which, so what I'm meaning is this distance is x0. We are cutting a section here. This distance is x. So W of x is a times x minus x0. So the loading itself is like this, and here what will happen is that at the end you will be given the value, let us say it is given as something like 10 kilonewtons per meter. So therefore this value of A, if this length is L0, then A will be equal to 10 divided by L0. So that is how, now in this case, when you calculate the shear force, V of x, we have said, is V of x minus V of x0 is equal to minus integral W of x dx, with x going from x0 to x. So therefore when you do this, what you will get is V at x minus V at x0 is equal to minus the integral of so you integrate this and that will give you the value of Vx. And what you realize is that this function now will become quadratic, because when you integrate x, so maybe we can do this. So what you will have is, I'll just write this again, V of x minus V of x0 is equal to minus integral from x0 to x a times x minus x0 dx. So this becomes equal to minus integral from x0 to x ax minus ax0 dx. So this becomes equal to minus of a times x square by 2 plus a times x0 times x with limit going from x0 to x. So it becomes minus a times x square by 2 plus a times x0 square by 2. Then we will get plus a times x0 minus a times x0 square and so on. So what we get is that expression for v will become quadratic and the expression for m this is equal to integral v dx. So this will become a cubic. So the function, if the loading is linear, then v of x will become quadratic and moment will become cubic. But you don't have to bother about integration. You can still use the way which we have done before, that we make a cut section, we find the total area under the loading up to the cut section, that will give us P, and we use the same formulas which we have used before. Only thing is, what you have to realize is, if it's a triangular loading, then the effective force will act at 2/3 from the base, and you use that to find the expression for the bending moment. You have to multiply P by zeta. So if you follow these basic rules which we have done, go through my lectures earlier, you will not make any errors. So that is how we we solve the problems of shear force diagrams and bending moment diagrams. Now one more thing. How was I so sure that this bending moment at the end will be 0? How am I so sure of this? Are there any cues to this? Is there any answer about this? Why should this bending moment be 0 at the end? And the answer to that lies in my loading. In my loading, I have a point support which cannot provide any moment. So therefore, at this end from the support, the moment is 0. So now, the question which I ask is, when will the bending moment at the end of the rod, at the end of a beam, when does the situation arise that the bending moment at the end of the beam is not equal to 0? And the answer is, if the beam has a fixed end, or if a point or concentrated moment of the acts at the end. Actually both of these are identical. So if you have a case like this, you have a beam like this, you have a force P. In this case, at x is equal to 0, bending moment will not be 0. Why? Because the support itself will put a, if this is the length L, so at the support there will be a moment which will be equal to PL, and so the moment, bending moment at the start, just after x is equal to 0, will be equal to PL with the appropriate sign. So similar to this, if you have a beam like this, so let me put it on a new page, the last thing, if we have a beam of this type, now here what will happen is, at the point B, in general, if it's a loaded beam, unless you happen to have some special case that this happens to be 0, at the point B, bending moment will not be 0. It will have some value which will be basically, in this case, if it's a loading like this, it will be, magnitude of the bending moment will be P times L, or as per situation demands. But if we have a beam like this, in cases like this, or in cases like this. In these cases, at A and B, bending moment will be 0. In this case, at A and C, bending moment will have 0 because at the end cannot be any moment. So these are again some tips. When you solve, when you write the equation and you have a beam like this and your moment equation comes out to be such that the value when you put x is equal to L does not go to 0. That means you have made some calculation error. So please work that out. Okay. So that I think that brings me to the end of this topic, shear force and bending moment. Now I have only, as I told you, about 1.5 lectures or even slightly less, and this I want to dedicate to the topic of friction. Now what we have is, when two bodies are in contact, then there is a contact force. So let's say there's a body A, there's a body B, which are touching itself at a point. So there's a point P1 on body 1, P1 on body 1 is in contact with P2 on body 2. So now, in general, when we look at the force which the bodies exert on each other, what we will have is, if I draw the free body diagram of body A, at the point P1, I will have a force. Will not have a moment because the bodies will be able to turn about each other, otherwise there will be a moment also. So we have a force. Now I'll notionally show the other body. In the free body diagram, I'll only show the body which we are talking of. Now what we do is, on this body of contact, this direction is what we term as the tangential direction, and the direction perpendicular to this is the normal direction. Is that clear? So first of all, we define our directions like this. Now you realize, if this is a three-dimensional figure, the tangential direction will actually be a plane, and perpendicular to that plane we will have normal. In case of a two-dimensional figure or two-dimensional situation, tangential line is only along one line and normal is perpendicular to that. Okay. So now what we say is that if we divide, if F is resolved along the normal direction and along the tangential direction, so therefore the normal component of F, this is what we term as the normal reaction. That is the meaning. You must have seen this term, normal reaction. And the tangential component of F, this is what we term as the frictional force, because what we will realize is that when we have dry contact, then the tangential component tries to hamper or tries to stop the, or I can use the word hinder, the relative motion of body 1 on body 2. So the relative contact just tries to make the two bodies to stick to each other, and that is why we use the word friction. It is called the force of friction, and in particular for dry contact we have this force of friction. So the force of friction, as we have discussed, will be the force in the normal direction. So we have done these things, we have discussed the force, we have discussed what is the force of friction. Now what we have is, let me explain for terms of these two contacts. Once again we had P1, P2 on the two bodies. Suppose, as we said, P1 is on body 1, P2 is on body 2. If velocity of P1 is equal to velocity of P2 at the time in question and at later times, that means the contact points on the two bodies have the same velocities at all times. This is what we call as a condition of no slip or no slide. That means both the points do not have a velocity with respect to each other. Now, what is the most obvious case of no slip? We see this pen. I'm seeing this pen which is on my hand. This pen is not moving. All the contact points between the pen and hand have the same velocity at this time and even at later times. So that means between the pen and my hand there exists a condition of no slip. They are not slipping. Next, what I can say is the second situation could be, so this was the first situation. So let's try to understand this, because this will have great implications on the laws of friction. So we have no slip. Now, does no slip always mean that the bodies cannot move? For example, here, if I say the pen has no slip, then the pen is not moving, the hand is not moving. Or both of them are moving with the same speed. As long as the pen doesn't move relative to the hand, it is still no slip. Both of them are moving, but both the contact points are having the same velocity. But then there is another motion where the pen can roll on my hand. If it's a curved surface, this will not happen in a straight surface. It can roll on my hand in such a way that velocity of the contact point is still zero. So that also is a case of no slip, but this is what we call as rolling without slip, and this will be explained more when we do dynamics. So, but no slip basically means the contact points are at zero relative velocity to each other for all times. Second, we have the case of slip or sliding between surfaces, and from the previous definition it's very obvious. The meaning of slipping or sliding is that the velocity of P1 is not equal to the velocity of P2. If I have this pen here and I push it like this, it moves like this, I push it in this way. So now the contact point on the pen and my hand, their velocities are different. The contact point has the velocity of the pen with which I am pushing it, it causes some velocity, and the hand is still. So that is a case when velocity of the contact point is not equal to the velocity of the second contact point, and that is the case of slip. Okay, but then we have a third very interesting case, and this is particularly interesting when we have friction, and that is that Vp1 is equal to Vp2 at t is equal to 0, but Vp1 is not equal to Vp2 at t is equal to 0 plus epsilon, where epsilon is a very small time later. That means if the same force is applied, then at the next instant the body will start to move. And let me illustrate this. Now I've taken a better thing in my hand, a duster. I am applying now. You can probably, can you see my hand? Okay, now I'm applying a force with my hand. So the force is very small. As it is applied, nothing happens. Now I increase the force. A particular value comes when I apply the force, this thing starts to move. And that is the point when the body has just started to move. This is what we call as impending slip. So these are the three conditions which come from kinematics, only from motion: slip, no slip, impending slip. Does everybody understand this? Well, the reason why these become important is because our laws of friction have got to do with slip, impending slip and no slip. What the laws of friction, we have what we term as Coulomb's laws, dry friction. So these laws are valid when the contact between two surfaces, there are two solid surfaces and there is a contact between them, there is no layer of fluid. If there is a layer of fluid between them, then we friction. But that friction, because of the flow of air, is what we term as viscous force, and that we will leave for fluid mechanics. Here we are talking of laws of dry friction. They were given by Coulomb's. Now once we use the word law, that means we cannot derive them. This is something which has been observed. Now the first law which comes is that the total force of friction between two surfaces is independent of the area of contact. If this duster is kept here like this, and if a small force is being applied, there will be a force of friction, and there will be force like this. Now if I turn the duster like this, and if these are not equal, if the same force is applied, the friction force will stay to be the same irrespective of the area of contact. I keep it like this and apply the same force, friction will be the same and it does not depend on the area of contact. Then we have the second law for friction, which is for low relative velocities, friction force independent of velocity. So that means if I have this duster, I push it with a very large force or I push it with a very small force, if it is moving, then the force of friction will not depend on the velocity of duster. Whether it is moving with a velocity of 1 meter per second or it is moving with a very fast 10 meters per second velocity, the friction force will not depend on the velocity, but this is valid only for low velocities. Low means the type of velocities we would deal with. Now comes the third law, which is very important and which is the most misunderstood. The law is very clear, but its application, I should say, is not well understood. So now what this says is that the force of friction, now you can easily see at any contact will divide the contact force R. So if this is so, the contact force R, this will be divided into two parts, a normal reaction and a friction force. So what this law tells us is that the force of friction is proportional to the normal reaction only for two cases: for impending slip or for actual slip. If the body is just about to slip, then the force of friction is proportional to the normal reaction. So force of friction is proportional to, let me write it fully, it's proportional to the normal reaction. And what we have is, in case if it is impending slip, the constant of proportionality is called the coefficient of static friction. So this will be the case when the body is just about to move, and in that case friction force is related to the normal force by the formula F is equal to mu s n. And in the case of actual slip, if the bodies are actually moving, then F is equal to mu k n or mu d n, where mu k and mu or mu d, this is the coefficient of, so mu k or mu d, this is the coefficient of kinetic or dynamic friction. But this is half the story. The other half, which is where most mistakes are made, for no slip, friction is less than mu s n. That means for a case of no slip, we do not have a relation between friction and normal reaction. We just get, there is no direct relation between friction and normal reaction. The mu n gives us a limiting value of friction. So that is how things are when we have friction and normal reaction, and this is how we work. Let me ask you a very simple question, and this I'll ask you to give me the answers of this. Some of you may have done problems of friction. We have an inclined plane at an angle theta. We have it like this. There is a block of mass m which is kept here. The coefficient of static friction is given as mu s. My question is, and please try to work out, what is the friction force which is acting on the block? The coefficient of the angle is given as theta, the mass is m, mu s is the coefficient of static friction. I want to find out what is the friction force on the block. It is given the block is at rest. So now to do this, let me first, I'll give you half the solution. Let's draw the free body diagram of the block. So this is the weight mg. We will have a normal reaction and there will be a force of friction because the block is tending to move down. Friction on the block will be up. I show this as F. So these are the forces which I have acting. This angle is theta. So what you can do is, some people like to work like this. You show n here, you show mg cos theta, this is mg sin theta, and we have friction. So this is the free body diagram. Now I'll again go back to you people. Let's go to some colleges. CE Pune will go at the end, not to start with, because they are the most active ones. I would like some more interaction. Let's see if there are, whichever colleges have some video. Okay, which college is this? RIT, RN. This is what, Ranchi, or you don't know? Okay. Yes, please. Somebody tell me the answer. What will be the friction force here? The coefficient of friction is given to be mu. Mu is the coefficient of static friction. What is the friction force acting on this block? Yes, any answers please? Yes, please. This RIT, RN. What will be the friction force?
दिसत नाही क्या आहे पुढे येते कॉलम
I have given 4 options. A, B, C, D. A is mu s mg sin theta. B is mu s mg cos theta. C is mg sin theta. And D is mu k mg cos theta. What is the correct option? Yes, AITM. Please tell me the answer.
B, sir.
B. Okay. Some other place. I'll RVIT. Okay. What is the answer to this question? I have put 4 options, A, B, C, D. Could you please tell me what according to you is the correct answer? Don't be hesitant. It may be wrong. It doesn't matter. Yes, please. What is the answer to this? Yes, I can see you, but why don't you give the answer? Do you have a mic with you? Otherwise, why don't you people just type it in? I think all the colleges have a typing in facility. Please give me the correct option A, B, C, D. Please start sending in fast. We are running out of time. आपके पास सिर्फ 1 मिनट का समय है. Your time starts now and it ends at 30 seconds later. Please give the correct answers A, B, C, D. Okay, LNMIT says it is C. Anyone else? Okay. More options, let's see. It can be correct, it can be wrong. I'm not saying either way. I want responses from other questions. C, Pune, you should give an answer. You are always very active. Please type in your answers or request me for a video. I will get you on the video. What is the answer? What, Bombay or Calcutta? C से क्या होता है? C से do we have some town? Calcutta तो क्या हो गया? What is C? Cat. Okay. Bombay or cat? This seems to be a divided house. Half of you are saying Bombay, half of you are saying cat. Is that right? Chennai. Okay, Bombay or Chennai? How many say Bombay? Raise your hand. How many say Chennai? Okay, are there any more answers, typed answers? Let's quickly see, otherwise I'll give the answer in a minute and then we'll stop. No typed answers? The correct answer here is Chennai. C. Because C. Okay. And the reason for that is, see here the block is just lying. It is in a state of rest. We do not know whether it is a limiting case or not. If it is a case of limiting motion, then both B and C will be correct. If it is just about to slip, then both B and C will be correct, and there we will get the relation mu s is equal to tan theta. So C is always the correct answer. B would be the answer if it was a case of limiting impending slip, then B would have been the correct answer also. But in this case, with the block is not moving at rest, then you look at the free body diagram, F is equal to mg sin theta. That's it. Now F is equal to mu n only when we have limiting case, otherwise only thing we can say is F is less than mu n. In the next class, I will continue, I won't have time to cover full friction, but we'll do 2 or 3 examples and I will explain some more subtle point. There is one more subtle point which I have to explain, and I will do that in the next class. And next class will be our last class. It has been a pleasure teaching you, but okay, one more thing which I had said was, okay, I'll just write this. There is my Google site, sites.google.com/site/ I'm continuing later my name, Sanjeev Sanghi. You can search on Google Sanjeev Sanghi, you will get this site. On this site, if you look out for notes on AML 100 or AML 110, these are the lectures which I teach to IIT students, to my students here. So lectures on mechanics, and you can click on the different lectures, you will be able to get the different topics, etc. here. So if you want some more material, you want to see more of this, you want to see more of my lectures which will also contain dynamics, you can always refer to these pages. Thank you.